Today we're going to go into how we have two ways that we commonly learn to represent the abstract representations of electron behavior in the electron cloud according to modern quantum theory. And that is the electron configuration and its corresponding box arrow diagrams. And then from there we will discuss how there are three rules that govern these representations, and they are based on actual experimentation about how electrons behave. But we're going to try to get very practical and basic here in how to write these and to not write these, and how tests will often ask you questions, which one of these configurations or arrow diagrams is wrong and why. So for our teaching tool today is we decided to use three incorrect ways of representing oxygen in electron configuration and this box arrow diagram. So the correct one we're going to put right here. So oxygen is the fourth element in the P block on the second row, and we can see if we add up the superscripts, it adds up to 8. So if we're looking at a neutral atom with an equal number of protons and electrons, your electron superscripts should add up to the atomic number of that element. That is, if we're dealing with a neutral atom. Ions we will deal with in a future video. For this week, we're just dealing with neutral atoms. So we start filling up, the first block, 1s2. And if we stop right there, that's basically would be helium. And then we start moving on to the second row of the periodic table. If you're looking at your periodic table, that brings us to lithium and then beryllium. So if we stopped right here, that would be beryllium. So we're moving to the right on the second row, and we get into the P block. And so now we start adding arrows to represent those 4 electrons in the P block for oxygen. So we start putting an up arrow. By tradition, the up arrow goes first, not the down arrow. This would be boron. And then here we would half fill the next P orbit, which is would be modeled as being roughly 90 degrees in orientation to the first P orbit, and that would be carbon. And we are doing this because Hund's rule tells us that electrons will spread out and occupy half orbits before doubling in a block. So we would not start doubling yet. And then we move on to what would be nitrogen, 2p3. We continue in that we start half filling the orbits in a block before moving on to the next block, which would double. And then we finally, in what would be the px orbit, we would double, and we have our 2p4. We've added that down arrow, and that is the correct oxygen configuration for electron configuration and arrow diagram. We did it this way because we were trying to follow these 3 rules that are taught in school: the Pauli exclusion principle, the off-ball rule, and Hund's rule. And for our purposes, Pauli is just another rule. So the Pauli exclusion principle, for the purposes of drawing these diagrams, is that electrons must have opposing magnetic spins, and we do this, represent that with up and down arrows. We're going to have 2 up arrows or 2 down arrows. And this is in keeping with the more general part of the rule, which is no 2 electrons can have the same quantum values. If you have the same spin, then you might want to, and you're in the same orbit, then you have the same 2 quantum values, which is a violation of that particular principle. The off-ball rule tells us that we cannot half fill a block before we're going to the next block. Remember, blocks are the S, P's, D's, and F's. So I could not half fill this one or this one and then go to that one. We would have to fill these first before going here. So that I'm making sure that we don't have these half-filled blocks, partially filled blocks. And then Hund's rule, which we mentioned just a minute ago, is that electrons will start, they don't want to be in pairs, they don't want to be together. They want to spread out into opposite, into different orbital zones so they can have autonomy, and this contributes to the structure of the electron cloud. But then, so we can't have this, we fill them in this way. All three of these rules are respecting another rule, which is there are never more than 2 electrons in a particular orbit. They can either be an unfilled, there's just simply no orbit happening in that zone, or a half filled, or a fully filled with 2. We will not have 3 or 4 or more electrons in a particular orbit. So sometimes you'll see tests that, you know, may have a box, you know, like this. You know, that would never happen. That's simply not going to happen. So in conclusion, when we're trying to match electron configuration to the arrow diagrams, we have to follow these 3 basic rules. The Pauli exclusion principle, which says no 2 quantum values may be the same for electrons in the same atom, which means that their spins must be opposing. They can't be both ups or downs. The off-ball rule, blocks must be filled before proceeding to the next block. See how this S block was not filled. And then Hund's rule, which tells us that electrons will spread out in a block to different orbits, so half filling the orbits before fully forming. As we can see, this was wrong and this is correct.